In this video, we're going to put everything together and see how we can use Laplace transforms to solve differential equations. Finally, we're going to see it put to practice. So here is a first-order linear differential equation. So you see it's obviously first order. We don't have a second derivative involved. It is linear. dy dt and y are separate terms. And it is in fact constant coefficient. A 1 in front of the dy dt and a 1 in front of the y. It is non-homogeneous. We have a term that doesn't involve y, and it's not 0. And in this case, it's t squared. We also have an initial condition. Okay, so first order linear constant coefficient. Now, this certainly falls under the category of a differential equation that we already know how to do. In fact, we already have two ways to do this. This is first order, right? So there were two ways of doing this. We could do this with the integrating factor approach, and whether or not we would run into some antiderivatives, but maybe we could do them. So that's an approach that might work. We certainly could do this using linearity principles and the method of undetermined coefficients. This one would definitely work with that approach. But now I'm going to show you yet another approach, Laplace transforms, and how this can work. Now remember that we don't really need another method to solve this particular one, but Laplace transforms will be, once we learn a little bit more, Laplace transforms will be able to solve some DEs that we currently don't have we have no approach to solve. So, but right now, just to get off the ground, we're gonna learn how to do this on one that we could already do. All right, and it'll certainly this very basic example will really get across the overall approach here. Very simply, what we do is we take the Laplace transform of both sides. As you see. Okay, now on the left-hand side, we are taking the Laplace transform of the derivative of y, and we just learned what that amounts to. That amounts to s y of s minus little y0, minus the initial condition for 0, which, by the way, we have a number for. On the right-hand side, we can first of all use linearity and write this as the Laplace transform of y plus the Laplace transform of t squared, right? And the Laplace transform of y, that's what we're calling y of s. And the Laplace transform of t squared, 2 over s cubed. Okay, so the Laplace transform has turned an equation, a differential equation for little y, and it was differential because it had a derivative in it, into an equation for big Y. And it's not a differential equation anymore because there are no derivatives here. That was the key thing, is that the Laplace transform turns derivatives into things that aren't derivatives. So now all we have to do is solve this equation for y of s, because you notice it shows up in two places, so we are going to have to get them over on one side together and solve. So in fact, let's do that. By the way, again, I already mentioned that we have the initial value y of 0, 1, so we can put in a 1 right there. Okay, so I'm going to bring this capital Y over. And I'm going to bring the 1 over to this side. Of course, I can factor out the capital Y. And then I'm just going to divide. So I get 1 plus 2 over s cubed, all divided by s minus 1. Now, let me just simplify this. This is kind of an ugly fraction right now. I'm going to multiply the top and the bottom by s cubed to kill this denominator. So this will be s cubed plus 2. And we'll have, well, actually, this one I won't even multiply out. You'll see why in a second. Well, actually, it won't matter. Yeah. S cubed times s minus 1. All right, so again, the differential equation for little y, we turned it into basically an algebra equation in capital Y, which we can just solve. So now we have capital Y, we have the Laplace transform of little y, the solution we're looking for. So now we just take inverse Laplace transform, right? The solution we are looking for to the original dE is a function whose Laplace transform is this. So we just have to now find a function whose Laplace transform is that. In other words, do an inverse Laplace transform. And if you're lucky, that's doable. That's not too horrible. So this is kind of a messy rational function, and so as I mentioned before when we talked about inverse Laplace transforms, the thing to do is to use partial fractions. And if you recall, I mentioned that I'm not going to really show too much of the algebra, the manual algebra for this, and I'm fine at this stage if we all just use technology to do that algebra move. And when you do it, either using your calculator or Wolfram Alpha or something along those lines, let me just rewrite it over here, we get 3 over s minus 1 minus 2 over s minus 2 over s squared minus 2 over s cubed. It's actually a complicated partial fractions because of the s cubed. You may not have done anything this advanced in terms of partial fractions in your Calc 2 classes. You might have, or possibly you didn't. So it's even more important that we're just letting our calculators do it for us. Okay, so now it's going to be a piece of cake to just sort of translate back to original functions in the world of little y. All these numerators, 3, 2, 2, and 2, are just multiples, right? So this is like 3 times 1 over s minus 1. This is 2 times 1 over s. So those multiples are fine. And then we just have to find functions whose Laplace transforms are 1 over s minus 1. Well, that one is just e to the 1t minus 2 times, and then 1 over s. That's the Laplace transform of just 1, so just minus 2 times 1. 1 over s squared is t squared, t. And 2 over s cubed, actually we need the 2 as part of this. That's not a constant multiple really. 2 over s cubed is the Laplace transform for t squared. And we're done. It's really a beautiful thing. It's a beautiful approach that we turned a differential equation. We sort of moved to a context where it wasn't a differential equation. So it's just algebra, and then we have to come back to little y again, doing an inverse Laplace transform. Okay. You could of course check, I won't do it on the video here, but you could check that this works. We certainly can check that the initial condition works. By the way, that's baked into it. It's not like an afterthought where you put in the initial condition at the end, like in our other approaches. That actually went in right at the beginning. So, but let's just double check that it came through. Y of 0 is supposed to be 1. If you plug in 0 here, right, we'll get 3 minus 2, and then that's 0, and that's 0. So yeah, we do get 1. That part's a check. And actually, this one, it's first order, so it won't take long. The derivative of our function, right, would just be 3e to the t. Derivative of 2 is 0, minus 2 minus 2t. And so the question is, do we satisfy dy dt equals y plus t squared? So here's dy dt. What's y plus t squared? So just take our differential, our proposed solution, 3e to the t minus 2 minus 2t minus t squared, and then plus t squared. And those go away, and we get 3e to the t minus 2 minus 2t, 3e to the t minus 2 minus 2t. Check. So yes, it satisfies the differential equation. It satisfies the initial condition. We know we are right. This is the answer. Okay, let's do another one. Here you go. Again, first order. We're just doing first order now. It's you can see it's linear and constant coefficient, but now the non-homogeneous term is a trig function. Here's our initial condition. All right, so we take the Laplace transform of both sides. The Laplace transform of the derivative, as always, is s times y of s minus the initial condition. Let me just go ahead and put in that 2 right now. Then we're going to take the Laplace transform of the right-hand side. So that'll be, again, using linearity, 4 times the Laplace transform of little y, that's big Y, plus 2 times the Laplace transform of cosine 3t. So we know what this is. This is s over s squared plus omega squared, but omega is 3, so 9. Okay, so now this is our Laplace transform version of the equation. We solve for capital Y, so we bring the 4 over. You see we'll have an s y of s and a 4 minus 4 y of s, so we'll have an s minus 4 y of s. I'm going to bring the 2 over. Okay, and then we divide by s minus 4, and we will have solved for the Laplace transform capital Y. I'm going to keep these, I'm going to divide s minus 4 into each of these terms separately. Not a big deal, but I think we might as well keep them separate. Yeah, so this guy I think is already ready to go in terms of going backward in terms of inverse Laplace transform. Right, that'll just be 2e to the 4t. But this guy is a little bit of a mess, so we feed that into a calculator or Wolfram Alpha and have that broken up by partial fractions. On the TI calculator, you use that expand command. And here's what I'm getting. Okay, there you go. So we got 3 terms when we break this up. And again, we're kind of letting technology take care of that algebra for us, which is really nice. Okay. Actually, I noticed that both this term and this term are a number over s minus 4. I can kind of think of this as 8/25ths, right, times 1 over s minus 4. And this is 2 times 1 over s minus 4. So I can combine those, and I guess that'll end up being 58/25ths 1 over s minus 4. Just moving that number off to the side now. And then we will have, again, I'll do the same thing on this one. It'll be minus 8/25ths s over s squared plus 9 and 18/25ths 1 over s squared plus 9. Okay, and so now we want to start thinking about inverse Laplace transform, going back to little y. Okay, the first term, as I said, I think was ready to go. 1 over s minus 4 is just e to the 4t when you bring it back to little y. So 58/25ths e to the 4t. That's that guy. Now this one, well, s over s squared plus 9, right? If we think this is like, this 9 is really 3 squared. I mean, that's where it came from originally, right? An omega of 3. This is cosine, right? So minus 8/25ths. That would be the Laplace transform of cosine of 3t. So we go back to cosine of 3t with that 8/25ths out front. We needed that s on top. When you have an s on top with this kind of quadratic on the bottom, that's going to be a cosine. Now, what about the 1 over s squared plus 9? Okay, well, it's almost but not quite like the Laplace transform for sine. Sine's Laplace transform doesn't have an s on top, which we don't have here, but it does have an omega. But omega is just a constant, so we can make that work. Remember, our omega here is 3. The omega, the omega squared is this number. So omega is definitely 3. So we need a 3 here. So what we could do is we could kind of steal a 3 from the number, right? We can reduce this down to a 6 and pull a factor of 3 over. So now this guy is matching the Laplace transform for sine of 3t. So 6/25 sine of 3t. And we're done. And that's it. And again, like I said, the initial condition is not, you don't have to put it in afterward. It was placed in the very beginning. So I won't do the check this time, but that would be the answer. It satisfies the initial condition, and most importantly, it satisfies that differential equation that we started with. So this is the Laplace transform approach. Still just doing first order, although we'll soon move to second order differential equations, and you'll see that it's not much more difficult. And we are still doing ones that we already knew how to do by other methods, I realize, but we are starting on those because they're a little bit easier. And we will eventually move to differential equations that we couldn't do without Laplace transforms.